Neural network is a function approximator. It is a system designed to map an input vector x to an output vector y. Through a series of non-linear transformations, we are not building a brain, we are building a complex statistical model capable of finding a relationship within high-dimensional data that standard algorithms cannot compute. Perceptron and linearity. The fundamental unit is a neuron or perceptron. Mathematically, this is the linear operation. The neuron takes an input vector and computes a dot product with the weight vector and adding a scalar bias. The weights determine the importance of the each input feature, while the bias shifts the activation function, allowing the model to fit the data that doesn't pass through the version. Without these two parameters, the network is a static. Activation functions. A linear combination alone is insufficient. Stacking linear layers only results in another linear model. To learn complex patterns, we introduce the non-linearity via activation functions. We apply functions like rectify linear units, which is relu or sigmoid to the weighted sum. This allows the network to approximate the arbitrary functions and curve the decision boundaries through the data space. This is where the actual computation happens. Forward propagation. In a deep neural network, these neurons are arranged in layers. During forward propagation, data flows from the input layer through multiple hidden layers to the output layer. Each layer performs matrix multiplication on the inputs from the previous layer. The hidden layers act as a feature extractors progressively breaking down the raw data like pixels or audio waves into higher level abstractions. The cost function. The network begins initialized with random weights. It will output garbage. To fix this, we quantify the error using cost function or loss function, such as mean squared error or cross entropy loss. This gives us a scalar value representing exactly how wrong the model is. Our objective is strictly mathematical, minimize this cost function to zero. Backpropagation and gradient descent. This is the engine of learning. Backpropagation, we compute the gradient of the cost function with respect to every weight in the network. Using the chain rule of calculus, we propagate the error backward from the output to the input. Once we have the gradients, we use an optimizer like stochastic gradient descent. We update the weights by moving them in the opposite direction of the gradient multiplied by the learning rate.